Picture this: a 22-year-old college dropout working in a woodshed behind his parents' house in Ohio. The year is 1886. He's mixing chemicals, running electrical current through molten compounds, trying to solve a problem that's stumped scientists for decades. His name is Charles Martin Hall, and in 8 months, he's about to make aluminum cheaper than silver, revolutionize manufacturing, and create an industry worth billions. But here's the crazy part. Aluminum was once more valuable than gold. The top of the Washington Monument, finished in 1884, is capped with aluminum because it was the most precious metal available. Napoleon III served his most honored guests on aluminum plates, while everyone else used gold. Extracting aluminum from ore was so expensive that it cost $300 per pound, roughly $15,000 today. Today, we're going inside Alcoa's Massena operations in upstate New York, one of America's oldest continuously operating aluminum smelters. This facility has been transforming electricity into metal since 1903. This is the story of how a college student's woodshed experiment became the massive industrial process that changed the world. Let's start with Charles Martin Hall's breakthrough. In 1886, he discovered that dissolving aluminum oxide in molten cryolite, then running electrical current through it, causes pure aluminum to separate and sink to the bottom. The process seems simple now, but it took years of failed experiments, burnt equipment, and skeptical professors telling him it couldn't be done. Here's what makes the story even more remarkable. On the exact same day, Hall succeeded in Ohio. A French chemist named Hall-Héroult independently discovered the identical process in Paris. Neither knew about the other. Both were 22 years old. Both filed patents within months. The coincidence is so extraordinary that today we call it the Hall-Héroult process, crediting both men equally. Hall's discovery dropped aluminum prices from $300 per pound to just 50 cents within a decade. But turning a woodshed experiment into industrial production required enormous amounts of electricity. And that's where Massena, New York, enters the story. Massena sits on the St. Lawrence River, one of North America's most powerful waterways. In the early 1900s, entrepreneurs recognized that the river's massive flow could generate huge amounts of hydroelectric power, perfect for aluminum smelting, which consumes staggering quantities of electricity. The Pittsburgh Reduction Company, which later became Alcoa, built their Massena smelter in 1903 specifically to access this cheap hydropower. The location was strategic. Close to Canadian power sources, near shipping routes, and positioned where electricity costs made aluminum production economically viable. Today, the Massena operations complex sprawls across hundreds of acres along the river. The facility doesn't mine aluminum ore here. Instead, aluminum oxide, also called alumina, arrives by rail from processing plants in the southern United States and abroad. This white powder is the feedstock that becomes aluminum. The transformation happens in massive buildings called potlines. These aren't your typical factory floors. We're talking structures several football fields long, filled with hundreds of electrolytic cells arranged in series, each one a precisely controlled chemical reactor operating at extreme temperatures. Each cell, called a pot, is a giant steel shell lined with carbon, roughly 20 feet long. Inside, molten cryolite mixed with alumina sits at 1,760 degrees Fahrenheit. Massive carbon anodes hang down into the molten mixture from above. These anodes, some weighing over a ton each, conduct electricity into the bath. The electrical current flowing through the molten cryolite causes a chemical reaction. Aluminum oxide splits apart. Pure aluminum collects at the bottom as liquid metal. Oxygen combines with the carbon anodes, slowly consuming them and releasing carbon dioxide. The amount of electricity involved is staggering. A single potline might draw power equivalent to a small city. Massena's smelter consumes roughly 400 megawatts at full capacity. That's enough to power over 300,000 homes. The electricity cost alone represents 40% of aluminum's production cost. This is why aluminum smelters cluster near cheap power sources. Massena benefits from hydroelectric rates that make production economically viable. Without that affordable electricity, the facility couldn't compete with smelters in places like Iceland or the Middle East, where energy is even cheaper. Inside the potlines, the process runs continuously, 24 hours a day, 7 days a week. You can't just shut down a pot. The molten bath must stay liquid. If it solidifies, the entire cell is destroyed and must be completely rebuilt, a process costing hundreds of thousands of dollars and taking weeks. Workers in protective gear monitor the pots constantly using computerized control systems. Sensors track temperature, electrical resistance, and chemical composition. Automated systems add fresh alumina every few minutes, maintaining the perfect ratio for efficient aluminum production. Every day or two, workers tap each pot to remove the accumulated aluminum. A specialized machine pierces the carbon crust floating on top of the bath, inserts a vacuum tube, and siphons out molten aluminum at over 1,800 degrees Fahrenheit. The glowing metal flows through heated channels into crucibles, large containers that hold several tons. Here's something most people don't realize. It takes 4 to 5 pounds of aluminum oxide to produce 1 pound of aluminum. The oxygen doesn't vanish. It combines with the carbon anodes, which slowly burn away and must be replaced every few weeks. A single potline can consume hundreds of carbon anodes per year. The molten aluminum from the pots still contains impurities. It goes to the casthouse, where workers further refine and alloy the metal. Furnaces reheat the aluminum, allowing dross and impurities to float to the surface where they're skimmed off. Alloying elements like copper, magnesium, or silicon get added depending on the final product specifications. Then comes casting. Massena produces several forms. Some aluminum gets cast into massive ingots weighing over 20 tons, destined for rolling mills that will flatten them into sheet metal for aircraft, cars, or beverage cans. Other aluminum pours into smaller billets for extrusion into shapes like window frames or structural components. The most common product is the standard 22-pound ingot. Thousands stack in the yard, ready for shipment to manufacturers across North America. Quality control is intense. Samples from every batch undergo chemical analysis and physical testing. Aluminum destined for aerospace applications must meet extraordinary purity standards. Even tiny amounts of contaminants can compromise the metal's strength or corrosion resistance. Alcoa Massena has modernized dramatically over its 100-plus-year history. Today's pots produce 3 times more aluminum while using less electricity per pound than 80s-era cells. Environmental controls now capture emissions before they reach the atmosphere, meeting strict EPA standards. The workforce has evolved too. Where the facility once employed thousands doing manual labor, today several hundred skilled workers operate largely automated systems. Computer operators monitor dozens of pots from control rooms. Specialized technicians maintain complex equipment. Engineers continuously optimize the process for maximum efficiency. Massena's strategic importance became clear during World War II, when aluminum demand exploded for aircraft production. The facility ran at maximum capacity, producing metal for B-17 bombers, P-51 fighters, and countless other military applications. Aluminum's lightweight and strength made it irreplaceable for aviation. That wartime boom established aluminum as a fundamental industrial material. Today, global aluminum production exceeds 65 million tons annually. The United States produces about 1 million tons per year, with Massena contributing a significant portion. But the industry faces challenges: rising electricity costs, competition from cheaper foreign smelters, and environmental concerns about carbon emissions have forced many older U.S. smelters to close. Massena survives because of hydroelectric power access, skilled workforce, and Alcoa's commitment to U.S. production. The future of Massena and American aluminum production depends on innovation. Companies are developing new smelting technologies that reduce electricity consumption and eliminate carbon emissions. Using inert anodes instead of carbon could revolutionize the industry by producing pure oxygen as a byproduct instead of carbon dioxide. Recycling also plays a growing role. Aluminum is infinitely recyclable without quality loss. Melting scrap aluminum requires only 5% of the energy needed to produce new aluminum from ore. As recycling rates increase, primary smelters like Massena must adapt by focusing on high-value applications where recycled metal can't meet specifications. From Charles Martin Hall's woodshed to Massena's massive potlines, the aluminum industry has transformed civilization. The metal once more precious than gold now shapes everything from smartphones to skyscrapers, from aircraft to automobiles. Next time you crack open an aluminum can or board an airplane, remember, that metal was once impossibly rare. A young inventor's curiosity and persistence made it abundant. And facilities like Alcoa Massena continue that tradition, transforming electricity and chemistry into the lightweight metal that defines modern life. From woodshed breakthrough to industrial powerhouse, from precious metal to everyday material, this is Alcoa Massena. Thanks for watching. Hit that like button and subscribe for more incredible stories about the facilities that built America. See you next time.
Glass, it's in your windows, your phone, that beer bottle in your hand. But have you ever wondered how something so fragile starts as nothing more than sand? Today, we're going inside one of the most incredible manufacturing processes on Earth, where temperatures hotter than lava turn ordinary sand into the crystal-clear material that shapes our modern world. The story goes back over 4,000 years. Ancient Mesopotamians stumbled onto something amazing when they heated sand with certain minerals and got a transparent solid. But it was the Romans around 50 BC who really cracked the code with glassblowing. Then in 1608, English glassmaker George Ravenscroft changed everything by adding lead oxide to the mix, creating what we now call crystal glass. Today, the global glass industry produces over 130 million tons every single year, worth more than $160 billion. From smartphone screens to skyscraper windows, this ancient craft became absolutely essential to modern life. Let's head inside a modern glass factory and see how sand becomes glass. It starts in the batch house, where automated weighing systems measure each ingredient with precision down to 0.01% accuracy. The main ingredient is silica sand, about 70% of the recipe. Workers add 14% soda ash to drop the melting point, plus 10% limestone for stability. But here's the clever part. Most factories add up to 30% recycled glass to the batch. It melts at lower temperatures, cutting energy costs by 40%. Once precisely weighed, everything dumps into a specialized ribbon blender that ensures every particle is evenly distributed. Then it travels along sealed conveyor systems to the furnace. And this is where it gets intense. The furnace is an absolute beast, stretching over 120 feet long, 40 feet wide, and standing 3 stories tall. Inside, natural gas burners fire continuously at 2,800 degrees Fahrenheit, hot enough to melt steel. The flames switch sides every 20 minutes in what's called regenerative firing, where exhaust heat preheats incoming air, boosting efficiency up to 50%. Raw batch pours steadily in at 15 tons per hour. Over the next 16 to 24 hours, it slowly dissolves into molten glass. Workers monitor everything from a control room with over 50 thermocouples throughout the bath. Even a 10-degree deviation can ruin the entire batch. The molten glass gradually flows toward the conditioning zone, where temperature drops to exactly 2,400 degrees Fahrenheit, achieving perfect homogeneity. From here, different products take different paths. Let's follow flat glass first. For windows and car glass, the molten material feeds into a float bath, one of the most brilliant innovations of the 20th century. British engineer Sir Alistair Pilkington spent 7 years perfecting this process before its debut in 1959. And here's the genius behind it. Molten glass pours continuously onto a bath of molten tin, kept at exactly 1,050 degrees Fahrenheit. Glass naturally floats on tin because its density is only 2.5 grams per cubic centimeter, compared to tin's 7.3. As it spreads across the perfectly flat liquid metal surface, gravity and surface tension create glass with both surfaces perfectly smooth and parallel. The float bath stretches for nearly 200 feet. Modern lines control thickness by pulling at specific speeds. Pull faster, you get thinner glass down to 2 millimeters. Pull slower, you can create glass up to 25 millimeters thick. By the exit end, the glass is cooled to around 1,000 degrees and solidified enough to lift off without marking the surface. From the float bath, the ribbon enters the annealing layer, a temperature-controlled tunnel over 500 feet long. If you let glass cool naturally, thermal gradients would create internal stresses, making it weak and prone to spontaneous breakage. Instead, the layer cools it gradually over 2 to 4 hours. At the exit, automated cutting systems use diamond-tipped wheels to score the ribbon into massive sheets, often 10 feet by 12 feet or larger. But bottles and jars follow a completely different process. This is where the IS machine comes in, standing for individual section machine. Invented in 1925, it's still the backbone of container glass production worldwide. Molten glass flows into a feeder bowl where rotating orifice rings cut the stream into precise portions called gobs. Each gob is sheared by pneumatic scissors with split-second timing, weights controlled to within 1 gram. A typical line has 10 or 12 individual sections, each making up to 4 containers simultaneously. Here's where it gets wild. In the blank mold, a metal plunger pushes down while compressed air at 40 psi blows up from below, forcing glass against the mold walls. This creates a parison, basically a thick-walled preform with the bottle's neck already shaped. Takes just 2 to 3 seconds. Then mechanical neck ring holders grip the parison, flip it upside down, and swing it to the blow mold in less than 1 second. Compressed air at 25 psi blasts through the neck, inflating it against the cooled mold walls. From molten gob to finished bottle in 8 to 12 seconds. A modern IS machine can produce up to 600 bottles per minute. Fresh bottles travel through an annealing layer for 30 to 45 minutes, cooling gradually. Then every single bottle faces automated inspection. High-speed cameras check for cracks and defects. Infrared sensors detect stress patterns. Bottles must withstand at least 90 pounds per square inch internal pressure. Any failures get crushed and recycled back to the batch house. For specialty items like wine glasses, skilled craftsmen still use traditional glass blowing at glory holes, small openings into reheating furnaces. They gather molten glass on a blowpipe and shape it with hand tools. A master glass blower can create a wine glass in 5 to 7 minutes. Now let's talk about safety glass. Laminated safety glass in your car windshield starts with 2 sheets of float glass with a layer of polyvinyl butyryl plastic between them. The sandwich goes through rollers at 190 degrees, then enters an autoclave at 280 degrees and 175 psi for 90 minutes. This fuses everything permanently. The result? Glass that holds together when shattered. In an accident, broken pieces stick to the plastic instead of flying around the cabin. That's why windshields spiderweb instead of exploding. Tempered glass for side windows takes a different approach. Regular glass heats to 1200 degrees, then high-pressure air nozzles blast it from above and below. Surfaces cool rapidly while the interior stays hot, creating compression on surfaces and tension in the core. This makes it 4 to 5 times stronger than regular glass. When it breaks, it shatters into thousands of small cubes with dull edges instead of dangerous shards. Here's something mind-blowing. Gorilla Glass and other chemically strengthened glasses used in smartphones go through an ion exchange process. The glass is submerged in molten potassium salt at 750 degrees for 8 to 16 hours. Potassium ions migrate into the surface, replacing smaller sodium ions. Since potassium ions are 40% larger, they create a compression layer, making the glass incredibly scratch and impact resistant. Quality control combines automated systems with human expertise. For flat glass, laser scanners detect defects as small as 0.1 millimeters. Random samples undergo destructive testing. Chemical composition gets verified using X-ray fluorescence spectrometry. Everything must meet strict safety standards. The environmental impact has improved dramatically. Modern regenerative furnaces are 30 to 35% more energy efficient than those from the 1980s. And here's the crazy part. Glass is infinitely recyclable without quality loss. That beer bottle you recycle can become a new bottle, a window, or fiber insulation. Recycled glass melts at lower temperatures, reducing energy consumption by 40%. Some plants now run on 90 to 100% recycled glass. After manufacturing, flat glass often receives low-E coatings that reflect infrared heat while transmitting visible light, cutting heating and cooling costs by 30%. Container glass exits production lines at up to 1,000 bottles per minute, packed into boxes and stacked on pallets by robotic systems. The glass industry continues pushing boundaries. Researchers are developing ultra-thin flexible glass, less than 0.1 millimeters thick for foldable smartphones and rollable displays. New formulations create transparent materials strong enough for military applications while remaining optically clear. From ancient Mesopotamian workshops to cutting-edge research labs, glass has traveled an incredible journey. But at its core, the principle remains unchanged. Heat sand hot enough, add the right ingredients, and you create one of humanity's most versatile and enduring materials. So next time you look through a window, drink from a glass, or tap your phone screen, take a moment to appreciate the 4,000-year-old craft and modern precision engineering that made it possible. From sand to something extraordinary. Thanks for watching. Hit that like button and subscribe for more fascinating looks at how everyday things are made. See you next time.
Los Angeles, 2 a.m. A Toyota Prius sits parked on a quiet street. 2 figures slide underneath with a battery-powered angle grinder. 90 seconds later, they're gone. So is the catalytic converter. The owner won't discover the theft until morning, when their car starts sounding like a lawnmower. The damage, $1,500. The reason? A few grams of palladium, a metal more valuable than gold, platinum, or diamonds. Welcome to the world of palladium, the rarest and most valuable metal most people have never heard of. Every single car on the road contains it. Your smartphone has it. Medical equipment depends on it. And there's so little of it that total annual production worldwide wouldn't fill a standard shipping container. Today, we're going underground to see how America mines, processes, and refines this precious metal that's literally worth its weight in gold times 2. This is the story of palladium. Let's start with why you've probably never heard of palladium despite it being everywhere. The story begins in 1803 when English chemist William Hyde Wollaston discovered a strange silvery metal while refining platinum ore. He named it Palladium after the asteroid Pallas, recently discovered that same year. For over a century, palladium was a laboratory curiosity. Pretty, rare, interesting properties, but no real use. Then came 1970. American cities were choking on smog from automobile exhaust. Lead, carbon monoxide, nitrogen oxides. The air in Los Angeles was so bad that children couldn't play outside on bad days. The Clean Air Act forced automakers to drastically reduce emissions. Engineers needed a solution fast. They discovered that palladium, along with platinum and rhodium, could catalyze chemical reactions that convert toxic exhaust into harmless gases. The catalytic converter was born. And overnight, palladium became one of the most important industrial metals on Earth. Here's the problem. Palladium is incredibly rare. We're talking rarer than gold, rarer than platinum. Annual global production is only about 200 tons. To put that in perspective, gold production exceeds 3,000 tons per year. All the palladium ever mined in human history would fit in a single Olympic swimming pool. And here's the crazy part. 85% of palladium goes into catalytic converters. Every gasoline car manufactured contains between 2 to 7 grams of palladium. With over 80 million cars produced globally each year, demand is massive and growing. So where does palladium come from? Unlike gold or copper, you don't find palladium deposits just sitting around. Palladium occurs almost exclusively as a byproduct of nickel and copper mining. The largest deposits are in Russia's Norilsk region and South Africa's Bushveld complex. But there's one place in the United States where palladium is the primary target: the Stillwater mine in Montana. This is the only significant palladium mine in America, and it's where we're going underground. The Stillwater complex sits beneath the Beartooth Mountains in south-central Montana. 2 billion years ago, molten rock pushed up from deep in the earth. As it cooled, dense metals like palladium and platinum concentrated in specific layers. The mine operates over 2,000 feet underground. Miners access the workings through a shaft that descends into solid rock. At the bottom, a network of tunnels extends for miles following the precious metal-bearing layer. Mining happens through a method called room and pillar. Miners drill blast holes in a pattern, load them with explosives, then retreat to a safe distance. The blast brings down tons of rock containing the palladium-bearing ore. Front-end loaders scoop it into haul trucks that carry it to the surface. Here's something most people don't realize. The ore is incredibly low grade. We're talking 2 to 10 grams of palladium per ton of rock. That means you need to mine and process 1 ton, 2,000 pounds, of solid rock to get less than 1/3 of an ounce of palladium. The economics only work because palladium trades at over $2,000 per ounce. The crushed ore travels to the processing facility where the real work begins. First stop, massive jaw crushers that reduce car-sized boulders into gravel. Then ball mills, enormous rotating drums filled with steel balls, grind the ore into powder finer than sand. Next comes flotation, a process that sounds simple but requires precise chemistry. Workers add specific chemicals to water containing the powdered ore. These chemicals attach to particles containing palladium and make them hydrophobic, meaning they repel water. Air bubbles blown through the mixture carry these particles to the surface, where they form a froth that gets skimmed off. The concentrated material still only contains a few percent palladium mixed with other metals. It goes to a smelter, where temperatures exceeding 2,500 degrees Fahrenheit melt everything together. The molten mixture separates by density. Heavier metals sink to the bottom. Lighter impurities float to the top as slag that gets removed. What remains is still a mixture of palladium, platinum, rhodium, nickel, copper, and other metals. This material, worth thousands of dollars per pound, ships to specialized refineries for final processing. Refining palladium to 99.95% purity requires sophisticated chemistry. The mixed metals dissolve in strong acids, creating a complex solution. Through a series of precipitation steps using different chemicals at specific temperatures and pH levels, each metal separates out one by one. Palladium precipitates as ammonium chloropalladate, a brick-red compound. Workers filter it out, heat it in special furnaces, and pure palladium emerges as a spongy gray powder. This powder gets melted and cast into bars, pellets, or wire, depending on customer requirements. The purity matters enormously. Catalytic converter manufacturers need palladium at exactly 99.95% pure. Any less, and the catalyst doesn't work efficiently. Any more, and the cost skyrockets for no benefit. So, what makes palladium so special for catalytic converters? It has a unique property. At high temperatures, palladium catalyzes the oxidation of carbon monoxide and hydrocarbons into carbon dioxide and water. It also helps reduce nitrogen oxides back into nitrogen and oxygen. Inside a catalytic converter, exhaust gases pass over a ceramic honeycomb structure coated with palladium. The metal doesn't get consumed in the process. It just makes the chemical reactions happen thousands of times faster. One catalytic converter will process exhaust for the entire life of the vehicle without the palladium wearing out. And this is why thieves love them. That ceramic honeycomb contains 2 to 7 grams of palladium, worth $60 to $140. The entire converter sells for $300 to $1,500 on the black market. It takes 90 seconds to cut one out with a battery-powered saw. Catalytic converter theft became an epidemic in the United States starting around 2020. Insurance claims skyrocketed. Some cities reported hundreds of thefts per month. The pandemic amplified the problem when palladium prices hit record highs above $3,000 per ounce. But catalytic converters aren't palladium's only use. Electronics use it in capacitors found in smartphones and computers. Dentists use palladium alloys for crowns. Jewelers mix it with gold to create white gold. Chemical plants use palladium catalysts to manufacture pharmaceuticals and plastics. And here's something incredible. Palladium absorbs hydrogen like a sponge absorbs water. At room temperature, palladium can absorb up to 900 times its own volume in hydrogen gas. This property makes it valuable for hydrogen purification and fuel cell technology. The future of palladium is complicated. Electric vehicles don't need catalytic converters, threatening to reduce demand. But hydrogen fuel cells, which need palladium, could offset that decline. Industrial applications keep growing, and supply remains constrained by geology. The United States produces only 12 tons of palladium per year from Stillwater Mine. Russia produces 80 tons, South Africa 70 tons. These three countries control 90% of global supply, creating geopolitical risk. When Russia invaded Ukraine, prices spiked on supply concerns. Recycling offers a partial solution. About 30% of palladium supply now comes from recycling old catalytic converters, electronics, and industrial catalysts. That percentage will grow as prices remain high. From 2,000 feet underground in Montana to the catalytic converter in your car, palladium's journey is remarkable. A metal so rare that total annual production fits in a shipping container. So valuable that thieves risk arrest to steal it. So essential that modern life as we know it depends on it. Next time you start your car, remember, hidden in the exhaust system are a few grams of one of Earth's rarest and most valuable materials, quietly cleaning the air with every mile you drive. From ancient geology to modern technology, from Montana mountains to your car, this is Palladium. Thanks for watching. Hit that like button and subscribe for more incredible stories about the rare materials that power our modern world. See you next time.